Good morning, students. I did leave an announcement on Blackboard. I didn't remind you about a signature assignment. I think you're probably getting used to those in your classes at San Jacinto College, and there is one for Calculus 2. And I did not remind you about it. I did have one student to actually turn it in. I think we had spoken about it during a conference hour. So I've given you extra time for that. It's not a difficult problem. It covers topics in chapter 7. And so, like I said in the announcement, you're welcome to work together on this, but I would like you to write up your own solution, and you will turn this in on Blackboard just as you have done in the past with other signature assignments. So I know you're busy, and it's just one extra thing to have to do, but like I say, it will count a quiz grade, so there is incentive to do it. It's not like it counts, 0.001%, so it does have a positive impact. So do look at that, and like I say, this will be turned in on Blackboard. There won't be anything that you turn into me. I will access your file that you upload to Blackboard. So again, there's extra time for that, and I appreciate your understanding of Professor Ron not remembering to remind you about it. Now, what we want to do today is to actually talk about some integrals that we can do with our integration tables, and also a Weierstrass substitution, and then from there go into some indeterminate forms. We've already talked about partial fractions and trig substitution, and those two techniques, along with the integration by parts, really allow us to generate an integral table. So that as you see these integral formulas that we use, you're going to think, oh, I could use this substitution, or I could use this technique. And so what I want you to be aware of is that as a future engineer or future STEM professional, you won't always have to start your integrals from scratch. You can use your integral tables and get to the punchline a little bit faster. Clearly, using an integral table requires that you understand integration, so it's a very good technique to do. What I want to do is share my screen and talk a little bit about these integral problems. Now, when it comes to doing the integrals with the tables, you're pretty much in control. You look at the particular example, and then you actually go to the table to find the form. So what I've done here, we've got formula 44. I went to your ebook, which is chapter B, and I printed the integral table. So as you actually look into your appendix, you will see certain forms here, and they're neatly written, and you can print them, or you can just keep them in your ebook for reference. The idea is that this is what we call a mini integral table. And like I say, we use patterns to recognize the type of integrand, and then we use the formula to finish this, just like I've done before with other examples that I've given you in class. But those were kind of quick, and I want to make sure that this technique is something you understand. So I want to do several examples of these, and then do the Weierstrass substitution, and then, like I say, make our way to the indeterminate forms. Now, the very first one is this particular integral. And what I've done is I've written down the formula, which I just showed you, that matches this particular integrand. And the idea is we just make everything table ready and we're good to go. Now, notice when we make the comparison, first we see that u is equal to x. So du equals dx. And then we have an a squared, which we clearly see is 49. Now, what's nice about this particular example is that the actual antiderivative is not extremely complicated. And you look at this and think a trigonometric substitution would solve it. So when you get bored of doing these, or you're tired of partial fractions or whatever, you can try to derive some of these formulas. I think you'll find them to be relatively straightforward. Once you build your techniques and your confidence level, then you can do what Professor Ron used to do, which in his calculus classes would sit down with the integral table because the professor said that we had to derive the formulas. But again, it's not the end of the world. So now we look at our integral, 49 x squared square root 49 minus x squared dx, and then we substitute. Now, the thing that I was saying before is that when we look at this particular problem, it's ready to go. The du is the dx, so we've got that lined up. We've got the a squared, the u squared, everything is ready to go. So we just don't have much to do. Now, of course, this 49, we just move out to the side. You don't have to put in so many extra steps, but the first time you do it, like we've done before, extra steps are better. So now when we look at this problem, we're ready to go. We've got everything set up for this actual antiderivative. So the 49 comes along due to the fact that it's just hanging out in the integrand. And so we have the additive inverse of a squared minus u squared. So this will be 49 minus x squared divided by a squared 49, in this case, times x plus a constant. So of course, now we see that the 49's absorb. So we get the additive inverse of the square root of 49 minus x squared, in this case, divided by x plus a constant. So you can see that the integral table can be a really handy item when you're working on problems. And like I say, there are all kinds of nice computer algebra systems that allow you to do integrals and things of that nature, and that's fine. Like I say, when I was at Texas A&M, we taught the students how to use Maple. But again, probably the best way to develop your skills is to use the integral table and to practice with that, and then that kind of use would actually be more meaningful to you. Now what I wanted to do, we did a rather lengthy integral. We had like a sine to the 6th power, a trig integral. We used the reduction formula. I just want to do another one that's a 4th power that's very similar to one you did in your WebAssign, and just work through it very simply, just as a reminder of what we've already done. So we had cosine of 10x to the 4th power. And now, when we use our formulas, if I look into the integral table, this is going to be formula 51. You've written this one down before. It's always good to kind of go back to something and just to see how much simpler it's going to look now. And the formula looks like this. We did the one for sine. We have the nth power of cosine of u du. And this gives us the cosine n minus 1st power of u times sine of u divided by n plus n minus 1 divided by n. And then we have we call this the reduction formula because we reduce the power by 2. So that's the formula that we were reminded of when we've worked with powers of sine and cosine, especially the Wallace formula that you saw on your quiz and your test, and obviously your homework. So now let's go ahead and make this table ready. So our particular integrand looks like this. And so when we compare here, this is a good formula to use. We have u equals 10x. So du is 10 dx. So this is easy to make table ready. So again, we're going to put in the 10 where we need it with the dx, and then actually pay for it with a factor of 1/10. Again, the nice part about doing the topics course, Calculus 2, is that we're forever reminded that the process going in the reverse direction is just more difficult. When we think of antiderivatives, we wish it were as easy. You know, when something's difficult, you wish that it could be that easy. But the idea is that it's just the nature of what we do when we're moving in the reverse direction. So now when we compare here, we have the fourth power. So again, if you want to write this in, I'll put this in here, n equals 4, just to kind of remind you of that. And so when we compare here, we're ready to go. We've got our u, we've got our du, and of course the 1/10 is hanging out due to the differential. So what does this give us? So we've got 1/10. And we did a long-winded problem like this. I wanted to do one that was a little bit shorter. And so we have cosine, n minus 1 will be 3, of 10x, sine of 10x, divide by n, that will give us a 4 downstairs, plus, and now we'll have 3 over 4, the n minus 1 over n. And then we have the integral reduced by 2, that is 4 minus 2 is 2. So we have cosine squared of 10x, and then times du, which is 10 dx. So we just write everything the same way each time. The du is just replicated throughout the problem. So now what we want to do is, again, simplify and then apply the reduction formula or our formula again. Sometimes they say just go ahead and apply the formula for the square because that's listed in the integral table, but we can just go ahead and work with this again. So this will give us what? A 1 over 40. So 1 over 40 cosine cubed 10x times sine of 10x. And now here we'll have the 40 downstairs and the 3. So we have plus 3 over 40. And now we're set up again. We have now n equals 2. So we can apply the integral formula again, just use another bracket if you like. And so now we've got n minus 1, which is 1. So we have cosine 10x sine 10x divided by 2, which is n. Then we have plus n minus 1 is 1, n is 2. And now we've got the integral. So of course we've got cosine to the 0 power. So that's by definition 1, and then we just have du, which is 10 dx. So now we can complete the problem. So we get 1 over 40 cosine cubed 10x sine 10x. And now, if you will, we'll go ahead and multiply this. We'll get a 3 over 80 plus 3 over 80 cosine 10x sine 10x. And then, of course, here we have the same. We have a 3 over 80 plus 3 over 80. And then, of course, the antiderivative here will just be 10x. And we could add a constant. Now, if you will, as you actually finish the problem, all we would need to do is just reduce this and we'll be good to go. So this would reduce. Of course, we could leave everything multiplied out. So we get 1 over 40 cosine of 10x quantity cubed. And my pre-cal students are getting used to this shorthand notation in trigonometry. It is a little weird at first, but then we live for it because it's nice. Of course, in your WebAssign, you have to abide by the parentheses. And then, of course, the tens will absorb and give us a 3/8. Now, of course, how much you choose to reduce your answer is completely up to you. If you leave things multiplied or whatever, WebAssign doesn't normally have any formatting restrictions on these problems except just the uppercase C here. So just remember, you all are getting to be professionals with this and you understand what you need to do. So just remember, the only mistake that you could make would probably just be a careless mistake, or maybe you try to fit a integral formula that doesn't quite match what you have. The issue with the integral table, again, is just making sure that we become good court reporters and copy them correctly. Now, here's another example. There's several in this particular section, and some, I don't know, some you may find a little bit dry and boring, but I want to do just several of them so that you get a good mix of them. The next one is actually a definite integral. So we've got the following. Now, like I say, as you work through the homework, just go ahead and check out your appendix, chapter B, when you look in your ebook, and you can scroll through them. And of course, you can enlarge the font and all to make them easier to read. In this particular example, you might look at this and say, well, this would be a good partial fraction problem. So like the last one, we thought, well, that would be a good trig sub. This one has a repeated linear factor in the denominator. Again, learning new techniques can also be a curse because that means we try to force the new technique on everything we already know how to do. So just be careful with that. It's easy to do. But as long as your technique is legitimate, you may say, oh, well, that was a simple integral. I didn't need to do all of this, but that's quite all right. Just be vigilant to make sure that you check your patterns out. And as long as the pattern is satisfied, you're good. Now, this one, we call these the A plus BU type. And so this is formula 7. So you look through your integral table and we get a formula 7 that looks like this. This is similar to one that you would derive with using partial fractions. So we have the following. We have u squared over A plus BU quantity squared du. So again, as you see a particular form, look through the table and match it up. And so it looks like, you know, excepting for some constants and all, we're pretty good. I mean, everything looks easy like the last one. And so this particular integral has the following antiderivative. 1 over b cubed. I'm just stating this from the table. This will be du minus a squared over a plus bu minus 2a natural log of a plus bu, absolute value. Now, a lot of times when you're working these problems, you can retire absolute values because the arguments are positive, and that's okay if you do or don't. Um, Certainly leaving in the absolute values doesn't make the problem incorrect. It's actually quite correct. But but don't worry about that if you're just trying to make sure your coefficients are correct. Now, when we look at the problem, if you will, let me go ahead and write this again here. So we have it a linear fashion. So you convince yourself that at least we've got a good candidate for the antiderivative. And then we just make some comparisons here. Note here that our A is 7 and the B is 2. And of course the U is X. So just making a direct comparison. So du equals dx. And then of course we have u squared, x squared in the numerator. So no other coefficients hanging out. So this one's ready to apply. Sometimes we look at this and say, okay, well, we look at the last one, we had that 1/10 factor, but don't be surprised if the problems are set up in such a way that you don't have any other coefficients to worry about. Now we can just go ahead and substitute and then of course apply the fundamental theorem 0 to 7. So again, this will be a real number. So this will give us, so we have 1 over b cubed. Okay, so we're going to cube b, that's going to give us an 8. And then we have a bu, so b times u will be 2x. And then we have an a squared, so a squared will be 49. And then a plus bu, that'll be 7 plus 2x. So there's just a lot of court reporting here, not very difficult. Minus, now we have 2 times a, so that will give us a 14, 2 times 7. Natural log, and then of course a plus bu, which is 7 plus 2x. I remember we did some special formulas with the trig sub, and those were pretty much like this, just kind of keeping track of the a squares and the b's and things of that nature. So this should remind you of that. And so of course we get a constant, but I don't need this, do I? I looked at the formula here. We're going to go ahead and put in our limits of integration. And of course, if you wrote the C in, it would just subtract anyway. So it's not incorrect to write that. It's just that we are lazy individuals and we just don't want to repeat ourselves unnecessarily. So yeah, just go ahead and put in the limits of integration. So now let's see what we get. So we have 1/8. So we use a big parenthesis because this is going to just multiply everything. So we have 2 times 7, that'll be a 14. And then we have a minus 49. And now again, we have a 7 plus a 14, so that's going to be a 21. Again, 7 plus 2 times 7 gives us a 21, minus 14, natural log. And again, we're getting the same things over and over, if you will. We're going to get a 7 plus a 2 times a 7, so that'll be a 21 also. So that'll be the upper limit. Then minus. Now for the lower limit, of course, with the 0 here, we get a 0. And then minus, we have a 49. And of course, the 0 here will just give us a 7. Minus 14, natural log. And of course, here with the 0, we just get the natural log of 7. So let's just go ahead and reduce this. We have 1/8. And so now notice here, we've got a 14. Of course, this we can reduce by 7. That'll just give us a 7/3. And then we have a -14 natural log of 21. We don't really need anything there. You can put the absolute values. Just maybe for now, just put parentheses if you like. We don't really need them, but with the numbers and all, it might be a little easier to understand. And then we have minus minus. So 49/7, that's just a 7. So plus a 7. And then we have minus minus again. So this will be plus 14 natural log of 7. So 1/8. Now, when we look here, we've got a 21, but we can get a common denominator, see what we can get out of that. So the 14, well, this is easy to see. The 14 plus the 7 gives us a 21. And we'll have to combine that with the 7/3, right? So let's do that. So 3, that'll give us a 63. 3 times 21, and then minus a 7. So 21 minus 7/3 gives us 63 minus 7/3. Just remembering 3 times 21 is 63. And now here we can just combine, if you will, with the law of logarithms. So this will be minus 14 natural log. So that would be a 7/21. Oh, and of course I need a plus here. Just the difference of logarithms. Again, factoring the 14. Of course, if the 14 weren't in front of both of them, we couldn't do that. We know there are plenty of restrictions here. And that takes care of this and this. So this will give us 1/8. And then, of course, the 7 from the 63, that'll give us a 56. And then we have plus 14 natural log of 1/3. Now, it doesn't really matter, you know, you've got the reciprocal here. Log of 1/3 is just negative log of 3, but you can leave it like that if you want. Notice the 8 will divide into the 56 to give us a 7. So we get a 7/3. And then we'll have plus 1/8 times a 14. And if you will, just go ahead and write this as a negative ln of 3 log of 1/3. So now we get 7/3. And then, of course, we can divide by 2. So that'll give us a 4 and a 7. So minus 7/4 natural log of 3. So when you look at an example like this, we really like the partial fractions because you had these really neat techniques to figure out the coefficients, clearing the denominators, using very convenient values of x and differentiating to kill everything off, so to speak, and apply 0 again. 0 is your friend, and we found that even if we had irreducible quadratic factors, the differentiation technique worked very nicely. But again, it takes some time. So here, this is a very nice use of the integral table, and then especially when you have a definite integral, so you can just focus on the computation. Again, not difficult, and it really doesn't matter here. I've been teaching trig to my pre-cal students, but I did a section on instantaneous growth and decay and the Newton law of cooling, which of course they don't have the calculus, but they have to have all the techniques that you calculus students have to have when it comes to logarithms and things. And so we would practice doing some things with these to make the calculations a little bit easier. So I thought this was a good example from the WebAssign where you have the use of the integral table. and the fundamental theorem of calculus that work really nicely together. Now, I want to say a little bit, there's some other examples that I want to do with the integration table. I want to do a volume of a solid of revolution. But before I do that, what I'd like to do is give you the classical example of the Weierstrass substitution. And in your actual book, you will have, I've got the integration table here. You will have rational expressions of sine and cosine. Like for instance, ladies and gentlemen, here, you'll notice that you've got, you know, plus or minus tangent, plus or minus cotangent, things like that. Again, you can use conjugate methods. On the previous page, we have some situations where we have 1 plus or minus sine u in the denominator, 1 plus or minus cosine u, where we have actually used, again, a conjugate method, and that's something you know very well. So those are things that we don't really need, you know, I mean, if we had to derive these formulas for this particular integral table, we know how to do this. We can just use conjugate methods. Now, so I just wanted to make you aware that you've already been creating an integral table. It's just that no one told you about the integral table, so you would get practice working the integrals. But one thing is that when you have integrals, say for instance, let me just give you an example. This will be our reason for doing this. If you clutter up the integrand with some coefficients, the conjugate method doesn't work very well. And here's an example. 1 over 2 minus 3 sine theta. This is even written up in the notes, but it's a really, really important example. And so basically here, what I'm saying is that if you need to use a more sophisticated substitution, you use it. If not, it's probably certainly much easier to you know, if you don't have an integral table, to use a conjugate method, because that's the quickest way to go without having to worry about any unnecessary difficulty. But this particular example here, ladies and gentlemen, doesn't fit the integral table. You've got this 3 here and this 2 here, and so conjugate methods would just not help you out at all. So what we do and what we use is the Weierstrass. So I'll just say, to solve this integral. And I learned about this as an undergraduate at Carolina. This is a very famous problem. To solve this integral, we use a substitution by Weierstrass. I think you've got the same problem in your WebAssign. And the substitution is actually a formula from your pre-calculus days. And you won't be surprised. Well, the formula won't surprise you. You're just wondering why it actually works. And the first time I saw this, it was you know, eye-opening, so to speak. It's like, wow, this actually does work. So I'm gonna use the standard derivation. So we're gonna say u is equal to, and of course here we'll have to go to theta for our variable, but I'm gonna just go ahead and use x here for our derivation. And we can just rig the formulas if we need to use thetas. So this is a very famous formula from trigonometry. That is the half angle formula for tangent. And you actually derive this. I have a neat proof of this. This is actually sine x without the radicals. sine x divided by 1 plus cosine x. This formula kind of blew everybody away because when you think about the half angle formulas, of course, you think about the concomitant radicals that make the plus or minus that make it difficult. This formula is devoid of radicals, devoid of plus and minuses. So this is a major result in pre-calculus. And so the idea here is that we can actually use this to rig a substitution to solve this integral. So the first thing we want to do is to square. So we just need formulas, and you're thinking, well, why are we doing this? We want to convert the integral into a rational integral, and then we get to use some of our formulas that we've already derived from the integral table. So if we square, we get u squared equals sine squared, and then we have 1 plus cosine x quantity squared. You can see where these go because aside from this, you probably don't remember this formula, but aside from that, everything else is going to be very, very straightforward. I remember high school pre-calculus with Dr. Tremblay. I don't know if we covered this or not. He asked me when I got back from my fall semester, how was math? I said, it was difficult. I said, but you know, it is what it is. He said, exactly, that's what I expected you to say. So now we say that sine squared is just what? 1 minus cosine squared, the fundamental identity. And now, of course, we can factor the difference of two squares. So we have 1 minus cosine x, just basic factoring, 1 plus cosine x. And then we have 1 plus cosine x quantity squared. Now, of course, we can retire one of the 1 plus cosine x. And so this will give us 1 minus cosine x divided by 1 plus cosine x. So when you actually look at this, you're thinking, okay, we've got linear in the cosine term, so we can solve for cosine. So we have u squared equals 1 minus cosine x divided by 1 plus cosine x. And that's how we can develop a rational function in u. So now when we cross multiply, so this will give us 1 minus cosine x equals u squared plus u squared times cosine x. So the idea in this particular case is we want to be able to, again, make a rational function to replace cosine x. So again, when we cross multiply, we get u times 1 and u squared times cosine squared, or excuse me, u squared times cosine. So now we can get all of our cosines together, if you like. So equivalently, we'll have, let's take the 1 minus u squared, or the u squared over here, and write it on the left. And then take the cosine over here, and this will be cosine x. And we factor the cosine, we get a 1 plus a u squared. So I just transposed. The u squared comes over to give us this. The cosine comes over, and then we can factor the cosine here and here to give us 1 plus u squared, and then we can solve for cosine. So cosine x will just give us 1 minus u squared divided by 1 plus u squared. So there's a rational expression for cosine x, which again is an improvement. Now, all we have to do, because this is usually for rational expressions in sine and cosine, we need a sine, and then we just need a differential and we're good to go. So we can go back to the original problem to get the the sign. Now, notice here, when we made this substitution, we know what cosine is, and we've got sine, and we've got the u here. So back to the original equation. So back to the original equation. This is one derivation that's worth doing. We can't do everything, but this is a fun one, and it's worth knowing. So now when we look at this, we have u equals sine x, and then we have 1 plus cosine x, but we have a new form for that. We have 1 minus u squared over 1 plus u squared. So we can just go ahead and keep everything downstairs for now. I mean, since I started doing it this way, I'll just leave it that way. Not very neat, but it's fine. So you get a common denominator of 1 plus u squared. So this will give us 1 plus u squared plus 1 minus u squared. So now we have u equals sine x. Of course, the u squared is absorbed, and we're just left with 2 over 1 plus u squared. So now we can just cross multiply. So sine x will be 2 times u divided by 1 plus u squared. So again, these derivations are not difficult, but they're certainly not expected. So the first time I saw this, it was weird. And then of course, when I went to grad school, the professors at A&M didn't focus on this, but when I got to San Jac and opened up the Larson calculus text, boom, here it is. So I think every textbook has different topics that they discuss. But I thought this was an important one, and I gained a lot of respect for Dr. Larson as he included this in his book. Now the thing is, we're ready to go, because if we look at the original integral, we're going to need this, and then the only thing else is the differential. So note here also, if we apply the inverse tangent, x over 2 equals the inverse tangent of u. Equivalently, x equals 2 times the inverse tangent of u. And so now we can take differentials. So dx will just be 2. And then of course we get 1 plus u squared, 1 over 1 plus u squared du. Let's stick that up there. So now we've got all the ingredients that we need. So again, this is just meant to give you an idea of how you actually have to address integrands that don't have the best form. And this is, like I say, a very famous example that we want to finish. So now we can apply this work. So let's get a clean sheet of paper. So we want to go ahead and make the substitution. So let me write down the original integral. So we have the integral 1, 2 minus 3 sine theta. It's always good to show you something you're actually going to need it for, as opposed to just doing it blindly. So now just remember, when we set this up, I'll write this in red, u will be the half angle formula, tangent of theta over 2, like we had x over 2. I think in the notes I actually write this up in x. I think I just probably got lazy and didn't use the theta. But there's the substitution. Now you don't start from scratch, you just use the formulas that we just derived. So we have them handy. So now we have the integral. So first, if you will, we can go ahead and write this with the differential d theta. And I'm just going to write this down from what we've already worked out. We have 2 over 1 plus u squared du. So that's the d theta. And then downstairs we have 2 minus 3. Well, let's see. I don't want to put the 3 there. 3 times 2 is going to be 6. So that's going to be 6u over 1 plus u squared. So here's what I did. I just used what we derived. For the d theta, or the dx, I just used 2 du 1 plus u squared right there. And then for the sine, we have 2u over 1 plus u squared. So I have negative 3 times that. So that gives me a 6u over 1 plus u squared. So that's just using what we just derived. Let me get there. There we go. So now we can do common denominators, but first notice we've got a lot of clutter here. They're common factors all through here, if you will. So first, well, we'll get rid of them. So we've got a 2, 1 plus u squared. And here we're going to have a 1 plus u squared. So I'm going to go ahead first and do this. 2, 1 minus 3u over 1 plus u squared. So just factor the 2. So now the 2's absorbed. And then here get a common denominator of 1 plus u squared. So those are going to go away. They're going to absorb. And this will be a 1 plus u squared minus 3u du. So the 2's absorb. So the 1 plus u squared is absorbed. And this gives us the integral 1 u squared minus 3u plus a 1. And we can just put the du right there. So go ahead and digest that. The fact is that most students look at the fractions and stuff and say, oh man, too many, it's like partial fractions all over. But notice, we are transforming this. This is basically a miscellaneous substitution. We're transforming this into something simple. Now, I'm going to bring up a formula that we've already actually computed, and I'll remind you of that. But this is just quadratic. Now, of course, you could use an integral table at this point, but that kind of defeats the purpose. I want to go ahead and do this all by hand. So now let's just complete the square. So we can use our formula that we derived last week. So now we're going to take half of this and square it. So we get u squared minus 3u plus, so that's going to give us a 9 over 4. That's going to be our perfect square. Now we've got minus, so now we've got plus negative 9 over 4 plus a 1. So it's simple algebra. So we have a du. And so, of course, now this will be u minus 3/2 quantity squared. And then, of course, here with the 4, we have 4 over 4. So 4 plus a negative 9 is a negative 5. And And now we just want to clean this up a little bit, get rid of all the fractional part. Makes it a lot easier to apply the formula. So now, of course, we've got a 1/4 here, but we've got a 1/4 downstairs. So first, go ahead and do this. With a common denominator. So we can factor the 4th now. So this leaves us a 2u minus 3 quantity squared minus a 5. And now, of course, the 1/1/4 is just 4. And this is starting to look like a formula that we already know. So we have 2u minus 3 squared. And of course, write that as a square. Now the formula that we did last week, I'm just going to write it where we can see it to the side here. And like I say, you can move the minuses and pluses around if you like. I think when you actually apply this, as I've done, I'm going to move turn the derivatives, excuse me, the differences around. So recall, so we don't have to use partial fractions. We have the integral of, now of course, now I need to write, this is already in u, so I'm going to write this in terms of w squared minus a squared. I know that looks weird, looks like an omega. So remember, we got 1/2a, and I'm just going to switch these around. We had a minus u divided by a plus u, but I'm just going to write it as u minus a, just using the absolute value. So the formula looks prettier. So if you wanted to, you can flip it around like we had last week, a minus u and a plus u, same difference. So this was a earlier result. So what's beautiful about this problem is that, you know, like I say, when I say do it completely by hand, I don't want us to get crazy, because I mean, we put the time to derive this, so I don't think we're, you know, remiss in using it. But notice now we see that the w is just 2u minus 3. I rarely write all this down. I don't change everything to w. We just make it table ready. And dw or d omega is just 2 du. So we'll make this table ready and then use our formula. So we need the 4/2 du, excuse me, 2u minus 3 quantity squared minus square root 5/2. Now, of course, we just get a 2 here. This is table ready, so we can go right to here. So we get 2. And let me put this here. The a is square root of 5. So that's all kind of the parameters that we need. So here we've got a 4/2 is 2. Then we have to have 2a, so we get 2 square root 5. So that's this right here. And then we get natural log. Oh, forgive me. You all are thinking, Professor Ron, math always corrects us. I mean, that, you know, that is, you all do your WebAssign. You know what I'm talking about. Natural log, yeah, of course. So now we have the natural log And I guess I should stick to my original variable, the w's. So we get w minus a. So we get 2u minus 3 minus a. And then we get 2u minus 3 plus a. And now we just want to make this look user friendly. So u started out here, tangent of theta over 2. So we'll just write this in the original variable. Of course, the 2's absorbed. This is just a long problem. Of course, you could throw this into a nice, I'm sure, Maple or MATLAB, and it give you a nice answer, but it would probably write it in terms of hyperbolic functions and all kinds of craziness. So here, 2u, so that'll give us a 2 tangent theta over 2. Minus 3 minus root 5. And a 2 tangent theta over 2 minus 3 plus root 5 plus a constant. So this doesn't really look a whole lot. I mean, I guess once you get to this point here, you're like, okay, yeah, this is starting to look like, okay, I see why you did this. With the conversion here to the rational function, we just get 1 over a quadratic, complete the square, and so we're ready for this formula, so to speak. Quadratics we can deal with. And so when we recall this particular formula in this particular case, since I was already using the u here, I wrote it in terms of w eventually. So, and of course, remember the natural log. So again, this was the first thing I talked about with the partial fractions, because this particular integral and its negative, the negative of this would be switched around, occurs all the time. You're going to see this over and over again. You will eventually just commit this integral to memory. And so once we have that with a direct application of these parameters, the 1 over 2a and the 2's absorbing, we have this, and then written in terms of the original variable. So like I say, if I put an x here and an x there, these would all be in terms of x. But I decided to go ahead and leave it in the form that WebAssign gives it to you. So again, just remember, we don't always have to utilize the more sophisticated substitutions. It may be very well that we can just get away with a conjugate method, or we can go right to the integral table and be fine. Now, a more sophisticated integral table would have these forms in it. Okay, would have these forms in it with these varying coefficients, and that would be like, oh, you know, that saves the day. I don't have to do this. But in our particular textbook, I think this is why Dr. Larson refers to this substitution. If it were just a matter of saying, okay, use the integral table, then there would be no use in going through this. The idea is that in order to develop integral tables, you have to come up with good substitutions. You have to come up with integrating techniques. Otherwise, the integral tables don't exist. So I thought this is a classical problem. Any person who takes calculus 2 should know how to do this. This is a classical example, and one that always finds its way into Professor Ron's Cal 2 class, and a fun example. So you should work through this, make sure you understand it. Again, you can apply this where you don't need it. It'll still work out, but I just want you to be aware of cases where you can get away with just the standard techniques, or in this case, where the standard techniques don't work. So there we go. That's a favorite problem and a fun problem. Now, I just want to say one thing about an application, and then you can enjoy your formulas. Like I say, I've got several examples here, but they start to get really repetitive, and I want to get on to the indeterminate forms. But there's a good example here, which is the following. It reminds me of our college algebra days. So we have region bounded by the graphs. So we have the following region. It's a nice odd function. Y equals x times the square root of 9 minus x squared. And we only want part of it. So we're going to insist on y equals 0, the x-axis, x equals 0, the y-axis, and then of course x equals 3, just to confine this to the first quadrant. So this will be first quadrant. Or as we say in pre-cal when we're doing trigonometry, quadrant 1. Yeah, they're learning the pitfalls of not paying attention to signs. Trigonometry is just a sign game. And the unit circle is where it all begins. And you master the unit circle, then trigonometry is at your fingertips. But that's no easy thing to do. So now what we want to do is revolve this region about the y-axis. So revolve, and then we're going to use one of our nifty formulas. Revolve this region about the y-axis. And so what we're going to do, so we get a nice formula, is use the shell method. And then, of course, compute the volume of the solid of revolution. Compute volume of the solid of revolution. So now let's just get a simple sketch of this. This is easy. This is a nice odd function. The domain runs from -3 to 3. We're only really interested in the first quadrant. We had a trig problem like this one time before, and this is how you restrict. But we don't have to be Rembrandt here. Symmetry with respect to the origin. So we can mark off like a 1, a 2, and a 3. Go ahead and I'll just kind of dot in. Yeah, spread this out a little bit more. So I'll dot this part in. I'll draw this one. And like that. So that's in no man's land. This is the part that we want here because we have this. So we have y equals 0, x equals 0 in the vertical line. So we just want to restrict to this part here and forget that part. So notice we want to revolve around the y-axis. We have, in this case, x element 0 to 3. So there's the 3, a nice vertical tangent. And then, if you like, just pick an x. I'll do this in blue. Here's a given x. So the distance to the axis of revolution, we would use a little p, is just x. And then, of course, the height of the strip is just the function. So again, not difficult, but the integral that we actually get is maybe not the most user-friendly, maybe some trig sub, and we like trig sub, but we don't want to spend the whole time doing the trig sub, so we can use our integral table. And my friends, you can use the integral table whenever you need it. Knowing how to use it does require that you understand basics about integration. So that's a technique I'm teaching you. So now when you look at this, the volume, this implies the volume of the solid of revolution. Remember, we had that concomitant 2 pi from the difference of the shells, so to speak, 0 to 3. And then we have x times the actual, or the p times the h, that is the distance to the axis of revolution times the height of the strip. So this will be x times x square root 9 minus x squared dx. So this will give us a 2 pi 0 to 3 x squared square root 9 minus x squared dx. Now, when you look at this particular problem, you're thinking, okay, well, we need a nice formula. You know, we're going to go into the a squared minus u squared forms and use that. So here's what I've got for you. This is, I looked in the table, and this is formula 38. So let me write this down. Formula 38. So it looks like this. We have the integral u squared. It's going to match up with this one. A squared minus u squared du equals 1/8, and we have u times 2u squared minus a squared times the square root of a squared minus u squared plus a to the 4th inverse sine of u over a plus a constant. So that would be a big help in doing this problem. That is, we've got this nice integral formula that matches this one. We have the 1/8, we have the u, we have the 2u squared minus a squared, square root of a squared minus u squared plus a to the 4th inverse sine of u over a. So that would be nice to be able to use to put this problem to rest. So now our original integral, so we're just going to keep going here. So this equals, so I'm going to write this again so you can see it, 2 pi. So back to the problem, 0, 3, x squared, square root 9 minus x squared dx. So when we make the comparison here, we see that u is x, u equals x, so du equal dx. And then we have an a squared of 9. A squared equals 9. So we get all of that. So this is table ready. So this will equal, we're going to go ahead and fill everything in. This will be 2 pi times 1/8. So we get the 2 pi divided by 8. And now we can fill everything in. We have u as x, and then u squared, so 2u squared, that'll be 2x squared, minus a squared, which is 9, square root a squared, 9, minus u squared, which is x squared, plus a to the 4th will just be a squared times a squared, 9 times 9. So this is really nice. Main thing is just we have to make sure we copy this correctly. And then inverse sine of x over what? 9. Oh, excuse me. That's an A. Professor Ron, let me just write these down. So A will be 3. A to the 4th is 81. So we get x over 3. How interesting. And then we evaluate from 0 to 3. So this is like the other problem we did where we were grateful for the actual integral table. So we get pi over 4. So now we're going to substitute 3. So, well, that's going to die off right there. So let's write it out. So this will be what, 3. And then, of course, we have a 2 times a 3 squared. That's a 9. So that's going to be an 18 minus 9. But of course, here, this is going to be a 9 square root of 9 minus 9. So that goes away. So again, we have non-zero here, but of course, a squared is 9, or excuse me, x squared is 9. And so that's going to zero that out. So for the first part, let's just use parentheses here, plus 81 inverse sine. Now we have what, 3 over 3. So it's good. I see the a there. So that's inverse sine of 1, which we know. Minus, now we're going to substitute 0, but that's going to kill everything off. That'll be a 0 there. So 0, and that'll be what, 0 minus 9 times the square root of 9. Again, that's just 0. You can go ahead and fill that in if you want. Plus 81. And then, of course, the x over 3 will be 0. So that'll be inverse sine of 0. Again, that's 0. So a lot of these terms are fading away. They're being annihilated, but that's fine. I mean, we have to verify that and again, follow the formula explicitly. So we get pi over 4. Again, this term is 0, but now we have 81. And the inverse sine of 1 is pi over 2. But now over here we have minus 0, that's a 0, and that's a 0. So both of these are just minus 0. Oh, sorry. 81. 81. 81. So now what's that going to do? We're going to have an 81. We're going to have 2 copies of pi and a 2 times 4. So that'll give us what? 81 pi squared over 8. Now that's odd looking, but not surprising. So the beauty here is that this is a problem that we worked in chapter 7, or a type of problem we worked in chapter 7. And now we're seeing that we don't have to be afraid of the integrals that we basically generate. Before we were certain, okay, we can use some kind of technique we learned in calculus 1 or some geometric modeling to actually compute the integral. But what we see here now with the use of a nice integral table, we can actually complete the problem. So as you learn new techniques, you go back to old problems and they don't seem so bad anymore. But again, as we remembered, the actual evaluation, the actual fundamental theorem of calculus part 2 always keeps us busy. Lots of typing, lots of court reporting, and then we see a very nice result. So again, the calculus can be very explicit in the sense, like I say before, like I tell my pre-cal students, every step is essential. Every step is important. If we go back and check the formula 2 or 3 times to make sure we've written it down correctly and checking each step for typos, because they're so easy to make. So very nice example. Now, what I want to do is spend a little bit of time on indeterminate forms, which I'm sure if some of you had a previous class or exposed to it, you've talked about or you've worked with. What I want to do is to utilize some ideas that you talked about in Calculus 1 and actually generate some new theory. These are called indeterminate forms. Now, Dr. Larson used to put all of this in chapter 8, but then he moved it to chapter 5. I don't know. I guess it's okay. We still teach it in Calculus 2. But this is what we call indeterminate forms. I just wanted to spend a little bit more time with the integral table and how we can use that to push our understanding forward. And again, if you get tired or bored or whatever, just take the integral table and start deriving the formulas. You can use what? Trig sub, integration by parts, partial fractions. Now, the idea is that the basic forms for indeterminacy or indeterminate form, the basic forms look like this. That is, when we talk about limits of quotients, this is a very famous indeterminate form when we talked about derivatives, 0 over 0. We don't know what that is, but the rule or theorem is actually attributed to L'Hopital, but he was not the one who actually figured it out. It was one of the Bernoulli brothers, but it ended up in his first calculus text, and he credited the mathematicians who actually derived it. But L'Hopital, history has proven that his name is still attached to it. So I guess he got a freebie. And now, of course, another form that exhibits indeterminacy is infinity over infinity. Now, there are certain ways to take other forms that may not fit this. That is, we can rig other indeterminate forms to mimic this. But what this means is with these types of indeterminate forms, we have a particular theory, and it's called L'Hopital's rule. L'Hopital's rule. And this is based on the the Cauchy mean value theorem or the extended mean value theorem. So we can look at something like this. For instance, we could have the limit as x approaches c of f of x divided by g of x. If this fits one of these forms, then we can take the derivative of the numerator using the Cauchy mean value theorem and the derivative of the denominator and try again. That is, these are equal provided this limit exists. Provided the limit exists. And of course, in Cal 1, you learned how to do this without this theorem. And some students who actually already knew it would apply it anyway, which is fine. I mean, it's good to develop your algebra. But another example of this would be the following. For instance, if you have x passing to infinity, where you also meet one of these indeterminate forms, you can apply the same rule. And in the notes, I have expanded upon the theory of this. You're welcome to look at that. I won't test you on it, but you certainly are welcome to look through it. Lots of estimating, but very straightforward, provided the limit exists. So students will say, okay, so I take the derivative upstairs and downstairs and apply the limit again. If it happens that the indeterminate form still exists, then this is what do we call it? An iterative process. We can apply it again. As long as the indeterminate form exists, we can still apply L'Hopital's rule. So maybe we apply it once or twice or maybe even 3 times. The idea is that we're searching for a limit. And as long as we satisfy the hypotheses here, then we're good. So let me give you a very simple example of this, ladies and gentlemen. You're going to look at this and say, oh, you missed the days of easy math. So the limit as x approaches 9 of 7 times x minus 9, this is how the WebAssign introduces this, divided by x squared minus 81. Now, of course, if you're in Cal 1, then you look at this and think this is a function with a hole in it, but not all of these are functions with holes in them. Pretty much they are, but well, yeah, they pretty much are. I'm just trying to make it simple. But the idea here is that when we look at something like this and x is approaching 9, we see that the numerator is getting very close to 0. And then, of course, x squared minus 9 as x approaches 9. Same thing, we're getting the 0 over 0 indeterminate form. So the idea is that if we apply L'Hopital's rule, I mean, of course, you would factor and just get rid of the x minus 9, get rid of the issue, and then pass to the limit. But with L'Hopital, we can apply the theorem. You can say, okay, well, the derivative upstairs will just be 7, and the derivative downstairs is 2x. And now as we pass to the limit again, we're thinking provided the limit exists, this would just be 7 divided by 2 times 9, or 7 over 18, which would be the same thing that you would have arrived at had you factored. So the idea here is the L'Hopital's rule was actually valid in Calculus 1, but you didn't have it. So again, what you did was you factored here, and this is what WebAssign will say. It'll say, do it the old way, and now do it the new way. Now, the factoring techniques that you learned were extremely important because we know how important that algebra is. We have to do this. But the beauty of this is that now, in situations where we can't factor, we have an out. Now another example, and you'll have several of these, another example that you saw in Calculus 1, which was a special limit. X approaches 0 of sine of 2x over sine of 3x. Now, when you look at this, you're thinking, well, the special limit was, what did we have? We had a special limit. You can prove this using geometry and the squeeze theorem. You have the limit as x approaches 0 of sine x over x. Basically, the x and the sine x grow at a similar rate. When x is close to 0, you get 1. Okay, so you're thinking you would rig this problem with a 2x and a 3x to write this twice and then pay for it. Okay, well, that's true, and that's a valid way to do it, and that's how it's taught at that time. But notice, as x approaches 0, this is why you had to do something here. You can't substitute. I mean, clearly that's no good. But here you see that as x approaches 0, we get the so-called indeterminate form 0 over 0. This occurs quite a bit. This does occur also, but the initial examples are pretty much this. And so then you're thinking, okay, well, I can take limits. L'Hopital's rule says maybe it equals this, possibly, if the limit exists. So let me try that. So we're going to say L'Hopital limit. And of course, you can use the old techniques. They're fine too. And please don't forget them. We'll take the derivative here. So that will be what? 2 times the cosine of 2x. And then, of course, 3 times the cosine of 3x. I mean, this is like really easy. I'm sure you're probably thinking that this would have been so helpful in Calculus 1. Well, now, of course, as x approaches 0, the cosine is defined there. We just get 2 times 1, cosine of 0, and 3 times 1, which is 2/3, which would have been the same answer you would have achieved using this technique. So the idea is the L'Hopital's rule is the Cauchy mean value extension that uses calculus. That is, we have to have a C1 function in the neighborhood of C or we've got to have a function that at least is well behaved at infinity for this to work. And the beauty of this is that we are really good at taking derivatives. Integrals are a lot harder, but derivatives are easy. So let's look at an example that's a little bit less simple. Let's see here, there we go. Every time I move things around, things move, and I don't like that. Let me give an example here. Let me get a new sheet of paper so Professor Ron has a little bit more room. So say, for instance, we're in a Cal 1 class and it's about over and you're ready to take your break. And you get something like this: y equals the natural log of x divided by x. And then you think, okay, well, your task here is to compute asymptotes and relative extrema. Compute asymptotes and relative extrema. Again, not very difficult, but a nice application of the new theory with L'Hopital. Again, we're taking the derivative of the numerator and the denominator. We're not using a quotient rule. It's not that at all. So don't even think quotient rule. So here, when we look at this first, we see the domain will just be the positive real numbers. And then, of course, when we think about these asymptotes first, vertical asymptote, as we approach 0 from the right, we just get x equals 0. We expect that. We get that for free just by taking pre-cal. And then for what happens as x tends to infinity. So we'll say the limit as x tends to infinity of ln of x over x. Well, this is a case where we know the log function is increasing, so we get large over large, so to speak. This is where we get indeterminate form, infinity over infinity. But we pretty much know or pretty much feel that x grows faster than ln of x, but whatever, we can apply L'Hopital. So by L'Hopital, we get the limit as x approaches infinity. Now, of course, the derivative of ln of x is 1 over x, and the derivative of x is 1. So this gives that, well, this is our bread and butter from Cal 1. I like proving this theorem. This is a fun theorem. So the limit as x approaches infinity of 1 over x, that's just 0. That's just basically using your intuition from calculus, pre-calculus, and then when you get to calculus, you learn what a limit at infinity is. And this is a famous example. We use this to rule with rational functions, so to speak. So now what we're seeing here is that we have a horizontal asymptote of y equals 0. And we used L'Hopital's rule to determine it. So again, L'Hopital's rule is your friend. And you're thinking after the integral table and the Weierstrass substitution, a whole lot easier. And for the most part, it is. So now for the relative extrema, let's do that. Let's just go ahead and say we've got our domain. It appears that we might have a relative max, but who knows? Let's look at y prime. So when we take the derivative here, we're taking the derivative of a quotient. So now we're back to Cal 1. So this will be the derivative of ln of x, which is 1 over x, times the denominator, minus ln of x, times the derivative of x, which is 1, divided by x squared. So of course the x is absorbed, so we get 1 minus ln of x divided by x squared. Now of course this is undefined as 0, but we know that that's not in the domain. We have a vertical asymptote. Another thing that we're noticing here is that this actually does have a horizontal tangent. As this can be 0 if and only if ln of x equals 1. Well, what's a logarithm? It's the power of the base. The power of e that equals x is 1. So equivalently, x is e to the 1 or e. My pre-cal students, you either know what a logarithm is from the pre-cal definition, and then in calculus 1, you learn more about it. But yeah, you always have to go back to that power of the base. So now what we see is we've got a critical number of the Euler base. So we can just use the first derivative test. So we have 0 and we have e and then the rest. So notice here, we've got what? 1 minus ln x over x. And so of course, if we take a number here, say like a 1/2, and we take something over here like a 10, well, notice that with the ln of 1/2, that's 1. And when you think about what we're doing here, and you think about how this works, let's go back to what we did before. Notice if we put in 1/2, this was the problem we did with the integral table where we had the logarithms. So if we do 1/2, we're just going to get 1 minus the natural log of 1/2, which is actually the negative natural log of 2. So that gives us 1 plus log 2 divided by 1/2, which is positive. So that's what I was thinking about when we did that problem. And then of course here we've got a nice increasing function. And of course the natural log of 10 exceeds 1. So this is negative. So by the first derivative test, this implies first derivative test that y has a relative maximum, as a relative maximum of y of e. And y of e is just log of e over e, which is 1 over e. And it actually turns out to be an absolute maximum. But again, very simple calculus and application of the first derivative test. The beauty of the calculus is that it's just fancy arithmetic. We just have to make sure that we do our arithmetic correctly. And so again, the use of the second derivative test would have just been kind of messy. It takes more time to take a second derivative than it's worth. So we just use the sign test from our first derivative test. So now, let's look at an example that has some geometry in it. Now, when you think about the sine x over x, you can consider a simple or similar problem that utilizes that geometry. And this is a nice application from your WebAssign of L'Hopital. So what I want to do is first consider the following, and I'm going to utilize this because I've got a nice drawing here. So I want you to look at this particular, this is Professor Ron's creation from the WebAssign. Now, this, go ahead and this part here, this is the unit circle. This is just in the first quadrant. So go ahead and draw an arc here. And again, you look at this problem and think this is how you did the geometric argument for the sine theta or sine x over x. And what we have here, we construct a theta. Again, remember 1 here and 1 here, unit radius. And we construct a theta just by drawing this particular segment through the origin. And the way this problem is set up, it's actually a L'Hopital's problem, where basically what we want to do is to consider point O, which is the origin, point D, that is from this point of intersection with the line and the circle, we drop the perpendicular, to form point D. And then, of course, the intersection of the unit circle with the x-axis, we call that point A. And then, of course, the intersection point on the circle with the line through the origin, we call B. And now, of course, the C up here is what it is. I don't even think I use this in the computation, but this is the vertical line through A, and of course, the line through the origin intersection. Now, what we want to do in this particular problem, this is a four-parter. First, we want the area of triangle ABD. So first, ABD. I put the red line here for the hypotenuse, triangle ABD. Now, in order to do this, we can actually take the difference of two triangles. Notice the triangle here that's not shaded can be subtracted from the larger triangle, which extends here to the red side. So if we say the area of triangle ABO, this larger triangle, minus the triangle DBO, we can get the triangle ABD. Now, the beauty of this is just base, 1/2 base times height. This just uses a lot of trig. But notice for the first triangle here, ABD, we have a base of 1, and by trigonometry, we have a height of sine theta. So we just get 1/2 times 1 sine theta. And now for the smaller triangle, this triangle right here, again, we're going to use trigonometry, but we only have the base, which is cosine theta, again using the unit radius, cosine theta, sine theta times 1/2. So the area of the triangle here with the red hypotenuse, ABD, is this expression right here, relative to theta. So just very basic geometry. So this, I like how WebAssign set this up. They did it in parts. And my drawing was so good, I wanted to use it. Now we want the area of the shaded region. So what Professor Ron did, in your WebAssign, this is shaded yellow. So we shade this and think, okay, well, how can I get the area of the shaded region? Look at this. The area of the sector is all of this, including the circular part. And then the triangle DBO, if we subtract from the area of the sector goes all the way through here. And if we subtract this angle or this triangle area from the area of the sector, we'll have the shaded part. Again, this is a very visual problem, but very much like the theorem proof that you see in Calculus 1. So we have area of a sector. Well, that's 1/2 r squared theta. Well, r is 1, so we just get 1/2 times 1 squared theta. That's simple enough. And then, of course, the area of DBO we just did up here. That's 1/2 cosine theta sine theta. So when we write this out, we get 1/2 theta minus 1/2 cosine theta sine theta. Now, think about what's going on here. As this theta goes to 0, what we're going to be interested in is taking the ratio of the shaded region to the triangle area ABD. And that's what we're going to do here. So it says the ratio of the area of triangle ABD to the area of shaded region. Okay, we want to write that because I think you're going to be surprised that it's actually a finite limit. And when you think about it, as theta gets closer and closer to 0, the red line and the circle demarcation start to blur. So this is a really nifty problem. So now look at this. If we do area of ABD, that's right up here, 1/2 sine theta minus 1/2 cosine theta sine theta. And then the area of the shaded region, that's right here, 1/2 theta minus 1/2 cosine theta sine theta. And then, of course, all the 1/2s absorb, And we get this, sine theta minus cosine theta times sine theta divided by theta minus cosine theta sine theta. Now, this part was just basic high school geometry and pre-calculus, nothing hard. Now, here's what I just described. We need to take the limit of this ratio as theta goes to 0, and that's what we're going to do. I wanted you to see that this was basically how WebAssign sets up the problem, and they just go through each step to have you set up the actual ratio from which we will extract the limit. So again, we have the area of this triangle with the red hypotenuse, area, divided by the area of the corresponding shaded region. I'll say corresponding shaded region, area of the shaded region. So this is a very unique problem. So let's compute this limit. So now we've done all the dirty work. So compute the limit as theta approaches 0. And in this case, it's really from above of R. But this is the limit as theta approaches 0. And I'll write it in, sine theta minus cosine theta, sine theta, divided by theta minus cosine theta, sine theta. So when you actually look at this, you're thinking, okay, well, let's see what we get. I mean, we can't substitute 0 because, I mean, there's 0, 0 minus 0, and 0 minus 0. So this is indeterminate. So we're going to apply L'Hopital. So the limit as theta approaches 0. And so now take the derivative, so we get cosine theta. And then the derivative of a cosine is negative sine, so we're going to get minus minus plus sine squared. And then the derivative of sine is cosine, so we get 2 copies of cosine with a minus. I mean, this is easy compared to the integrals, but very, very useful. And when you get to differential equations and transform methods, yeah, this L'Hopital will be really, really handsome addition to your techniques. Okay, derivative of theta with respect to theta, that's 1. And now we do the derivative of cosine is the negative sign, so the same thing again, we're going to get plus sine squared. We're getting the same thing, obviously. This is the same term. So then we get a minus, the derivative of the sine is cosine, so we get 2 copies of cosine squared, just like that. So that's like the same computation twice. And now we're gonna cheat a little bit because I like trigonometry and maybe you do too. This is just the negative of cosine of the double angle. So this is just minus cosine 2 theta. Remember, cosine 2 theta is cosine squared minus sine squared. And so if we have the additive inverse, we've got that. And then downstairs, we have the same thing. 1 minus cosine 2 theta. Now, when you look at this and you think, okay, well, are we home free? You know, do we have to do it again? Let's check. As theta passes to 0 from above, we get 1. And then, of course, here, this is just cosine of 0. So that's 0 up top. And then downstairs, the same thing, 1 minus 1, which is 0. So we've got 0 over 0, indeterminate. So let's plot L'Hopital again. As long as the hypotheses are there, we can apply L'Hopital. So the derivative of cosine is the negative sign. And then, of course, the derivative of cosine is the negative sign with the 2. So this is plus 2 sine 2 theta. And then, of course, downstairs, the derivative of 1 is 0. And same thing here. We just get 2 sine 2 theta. Again, the derivative of cosine is the negative sign, 2 negatives, chain rule, 2 sine 2 theta. Now, of course, we check again. What do we get? Pass to the limit, x approaches 0 from above. Well, again, 0, negative 0, plus 0, 0, 0 downstairs. Again, basically just replacing theta with 0. We still have indeterminate. So we can apply L'Hopital again. So now we've got what? 1, 2, 3, 4. So now the derivative of the sine, that'll be cosine with the negative. And now, of course, the derivative of sine is the cosine, but then, of course, the 2 multiplies the 2. So this is plus 4 cosine 2 theta. Now we're getting somewhere. And then, of course, the same thing here. The derivative of sine is cosine. With the chain rule, we have the 2 times 2. So we get 4 cosine 2 theta. Now it looks like we can pass to the limit. As theta approaches 0 from above, we're going to get what? Negative 1, and then we get a 4 times a 1. And then, of course, downstairs, we get 4 times a 1. So we get 3 over 4. So the thing that I wanted to mention is that when we look at the original geometry, we're thinking, okay, well, this is an interesting problem. I like working with sectors of circles and areas of triangles and figuring out areas. But when we look at this ratio, that is the ratio of the triangle with the red hypotenuse to the shaded area, we actually get a finite number. So what starts to happen is that we get a blurring of the separation of the triangle and the actual shaded region that does not become infinite. So it's interesting. I mean, lots of times when we have these, like the ladder problem that you did with the related rates in Cal 1, where you get, you know, the infinite descent. I mean, you get some crazy things going on with the mathematics, but here is actually very behaved, very behaved. So that's an excellent example, and thanks to the WebAssign for that. That's a beautiful example. Now, I want to look at a couple of things here. Lots of times when we do L'Hopital's rule, maybe we want to rig something. Maybe we don't really get the 0 over 0 or the infinity over infinity, but we're getting something that we can rig to make look like that. So here's a good example. Now we need these limits so we can do improper integrals on Wednesday. So that's why we need to do this. So here, let's look at this one. Find the value C that makes, that's a fun geometry problem. That's fun, some entertainment for Monday morning. Find the value C that makes the function continuous. And easy calculus too, easy Cal 1 calculus. Function continuous at x equals 0. Unless you took Cal 1 with Professor Ron, and I would always find a way to make it challenging, but it's all good. You do the work and then you live the dream. So we have e to the x plus x to the 1 over x when x is non-zero. And then, of course, c when x equals 0. So this is a situation where the L'Hopital's rule is indispensable, but it requires a technique that I don't believe you've seen before. or at least what we've done so far has been relatively straightforward. The indeterminate form, we take derivatives upstairs and downstairs, pass to the limit. If it does exist, we know we have the actual limit of the original function. So what we're seeing here is, notice, if we look at this, let's say y is the limit as x approaches 0 of e to the x plus x to the 1 over x. Let's start with that. And then when you look at this, you think, okay, x is approaching 0. So this is getting close to 0, and e to the 0 is approaching 1. And then, of course, 1 over infinity is 1 over 0 as x approaches 0. In this case, from the right is infinity or negative infinity. So this is where we've got something like this. We've got 1 to the infinity form, where you can switch out the plus and the minus, or you can write it this way. It doesn't change anything. That's an indeterminate form that we don't understand. So this is, like I say, indeterminate. So the minuses don't give us a problem so much. It's just that like you could have infinity over negative infinity. You still have the issue here in that we have no way of treating this. At least, I mean, you know, you could say infinity times infinity is just infinity. Or if you add infinity to infinity, that's infinity. That's determinate. But this we don't know about. So here's the technique that we use. We're just going to write. We're not going to let anything. We're just going to write the following. The natural log of y, and use the continuity of the natural log function. So we're going to write this, and hopefully, fingers crossed, be able to apply L'Hopital, because we'll rig one of the indeterminate forms that we started with. So this will be the natural log of the limit as x approaches 0 of e to the x plus x to the 1 over x. And then by continuity, we can just move the logarithm into this and use the power rule. So this will be the limit as x approaches 0 of the natural log of e to the x plus x 1 over x. This has no problem because these are nice positive quantities as x approaches 0. No issue there. We take logarithms of positive quantities. So this is basically continuity. Moving that limit in and out, that's the key. We learn all of this in Cal 1, even though at the time you probably didn't appreciate it. So now we're going to use the power rule. So that brings the 1 over x down, which we can write in the denominator. So the idea is, if y is an issue for us, we can use the continuity of the natural logarithm to investigate what's happening to the natural log of y as x approaches 0. Can it help us understand what's going on over here? And the answer is yes. And so now we look at this as x approaches 0. Basically now we've got the natural logarithm of essentially 1, which is 0, and of course x is approaching 0. So this is an indeterminate form here. And this is one of the original ones that we talked about. So when you have these rather obscure indeterminate forms, if we can rig them to meet 0 over 0 or infinity over infinity, we can apply L'Hopital's theorem. We don't apply it directly to this. We just try to make this look like this. And then we can apply L'Hopital. So now we do it. Very, very useful. This is the gap that we left behind in Calculus 1. It's like, how do we do this limit? What theory do we need? And this is it. So we have the limit as x approaches 0. And so now we just do the reciprocal. 1 over e to the x plus x times the derivative of e to the x plus x, which is e to the x plus 1. Very simple. And of course, the derivative of x is 1. Well, you know, lo and behold, that's good. So x approaches 0 of e to the x plus 1, e to the x plus x. And now, of course, we can pass to the limit. We just get upstairs e to the 0 plus 1. So this is 1 plus 1. And downstairs, we just get e to the 0 plus 0, which is 1. So we get 2, which is a bona fide limit. So the idea here is that by investigating the natural log of the so-called limit that we need to know, L'Hopital's rule has introduced a way to analyze. But now, of course, we have log of y equals 2. What's a logarithm? Power of the base. If and only if y is equal to e squared. If and only if the limit as x approaches 0 of e to the x plus x to the 1 over x power, in this case, is what? E squared. So when you actually do this problem, you say, okay, so then define c to equal e squared, and we're done. And so now if we define c to be equal to e squared, then of course this limit will equal the value at 0, and that just is the definition of continuity. So what you're seeing here is that the L'Hopital's rule turns out to be a blessing. Now, in the same vein, as we draw to a conclusion here, let's just go ahead and apply this to some integrals. So L'Hopital can be widgeted into a problem by using logarithms, or maybe we'll use the fundamental theorem. So let's let the limit as x approaches infinity of the following ratio. And we have the integral of 1 to x. This is a fun problem and an easy problem. E to the 4t minus 1. You're thinking, well, that a pre-cal student could do this. So now when we look at this problem, we have the limit as x approaches infinity of the integral from 1 to x of the natural log of e to the 4t minus 1 dt divided by x. Well, the logarithm and the exponential, natural exponential are inverses. So first, that we can reduce that. WebAssign was being good to you. So this will be the integral 1 to x of 4t minus 1 dt divided by x. Now, of course, this is a nice positive integrand on this interval as x approaches infinity. So it becomes larger and larger as x does. So this is just infinity over infinity. So what we're seeing here is that we get to use all the calculus that we already know, the properties of logarithms, properties of definite integrals or indefinite integrals, which we have at our disposal completely. And now, of course, we can take derivatives. So the derivative of the integral is just going to be the integrand evaluated, in this case, at x. So this is like first fundamental theorem. So this will be the limit as x approaches infinity of the derivative with respect to x, 1 to x of 4t minus 1 dt. I'll just go ahead and write it out. Go ahead and put all the derivatives in. Make it really formal. And so now by the fundamental theorem, we just have the limit as x approaches infinity. So in this case, we just get 4x, the integrand evaluated at the upper limit, 4x minus 1 divided by 1. So this is just the limit as x approaches infinity, 4x minus 1, which is clearly infinity. So we can actually do these limits, you know, again, applying calculus that we already have at our disposal. That is, when we did the geometry, we spent quite a bit of time just looking at the basic geometry and apply L'Hopital's rule. And now we apply calculus that we know to compute limits that would otherwise not be at our disposal using L'Hopital. And then of course here, using L'Hopital and the first fundamental theorem of calculus differentiating the integral, we have a very simple problem. So again, the reason we're doing these new types of limit techniques is so that we can apply them to improper integrals. Improper integrals will be the next thing that we do. And again, kind of a fringe topic, but when you take more calculus and you take more engineering and physics courses, you will do improper integrals. And of course, when you do transform methods. So why do we need them in Cal 2? When we get to some of the integral infinite series techniques, we're going to need to know how to do an improper integral, especially with the integral test. So go ahead and finish up your homework for the trig and the partial fractions, and we will complete chapter 8 next time with the improper integrals, and then we're going to use all of this stuff that we've learned and made us all much smarter to conquer sequences and series, which will, I think, be the most fun part of the class. So thank you for your attendance today. I know Monday is tough. Monday's always a hard day. I don't care how you slice it. It's just a difficult day. But thank you for your attendance, and everybody stay well. And if I don't see you at my conference hours, I'll see you on Wednesday. Take care.